Welcome back. So we're going to talk today about sampling distributions, specifically when our data is categorical. So we're dealing with proportions, what proportion of our population or a sample does a certain thing. So our objectives today to determine the parameters of a sampling distribution, to determine whether a sampling distribution can be described as normal, and to calculate and interpret probabilities. So let's get started. And I'm going to start by just reminding you what we talked about briefly in class, which is what is a sampling distribution. It is basically a collection of a large number of sample statistics, either means or proportions, of a given sample size. So the idea with the sampling distribution is that if I take a whole lot of samples of the same size from a population, we want to know what does the distribution of either the means or the proportions, depending on what type of data it is, what does that distribution of means or proportions actually look like on a graph? Why are they important? Well, a couple of reasons. One is that they give us an idea of what is typical for a sample of a certain size taken from a certain population. So if I want to know whether a certain sample mean or proportion that I got is considered out of the ordinary, a sampling distribution tells me what I can expect, and that would tell me whether that my sample mean or proportion that I got is significantly higher or lower than what I would expect. It helps me compare it to what is typical. We'll kind of see some examples of that as we go through. But today's problems are going to be all about dealing with categorical data, meaning that we're talking about the proportion of something. So what proportion of people have brown hair, what proportion of people can drive a car, categorical data, and proportions. So first, I want to draw your attention to our formula chart, which gives us these couple of kind of pieces of information. The formula chart tells us that if we have a sampling distribution for a proportion, that we can expect that that sampling distribution would have the following mean and the following standard deviation. So the idea behind this is that, yes, I could go through the process of actually taking a whole bunch of samples and then finding the proportion of interest for each sample and then physically graphing all of those sample proportions. But these rules come from a place of trial and error. Through lots of trial and error, statisticians of our past, we have discovered that these trends or these patterns tend to happen. So what the first thing is the mean. So this symbol is mu, and then it has a little p hat. It's kind of hard to see, but mu p hat is equal to p. This is telling us that the mean of that sampling distribution for proportions is generally equal to p, which is whatever the actual proportion is for the population. So when we take a whole lot of samples from a population and find the proportion for each sample and put those proportions on a graph, the mean of that graph is going to be equal to whatever was the original proportion of the population. The second thing is that the standard deviation of that graph is equal to this square root of p, so proportion for the population, times 1 minus p divided by n. Right? And again, this comes from lots of trial and error of statisticians in our past. The other thing that we would want to know about that sampling distribution is the shape. Is that shape going to be approximately normal? Is it skewed, etc.? And then the other thing is, how do we know that these rules and formulas will give us an accurate view of the sampling distribution? How can we be sure that this is truly what would happen in real life if we were to take repeated samples from the population? So there's a couple of rules, we call them assumptions/conditions, that we have to check or assume in order to trust the information from the formula chart, to trust those formulas and rules for this particular situation. First thing is that we really need to know that we took a random sample. This is avoiding bias. We want to make sure that the sample we are taking is representative of the population. So hopefully it's a random sample, but if not, we should be able to safely assume that the sample is representative. The second is that we have independence between trials, meaning that if we are sampling without replacement, that the sample size is less than 10% of the population size. We've talked about this a couple times before. This is just making sure that as I'm picking my sample from my population, that the proportion that we're dealing with doesn't change too much from one sample to the next. So sampling size has to be less than 10% of the population. And then the third condition is what we call the success failure condition. And this is what's checking for the shape. This will tell us whether that sampling distribution is going to look roughly normal versus skewed one way or the other. And what we check is, does n times p and n times q, q would just be 1 minus p. We see that shorthand a lot. It's just 1 minus p. So if n times p and n times 1 minus p are both at least 10, then that tells us that we are pretty sure that the sampling distribution is going to look roughly normal. Right? This also might be called the large counts condition in some books. So I'm going to go straight to an example, and we're going to go through a process of how I would solve a probability question and what are the steps that I have to take to solve that question. There's going to feel like a lot of steps on this example, but you will get better at it as we go through. So this example says that a polling organization asks a simple random sample of 50 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. So that right there, that's telling us that that is what's true for the population. So that is P. P in this example is 0.35. It's the percent of all the students who attend college within 50 miles of home. We're going to find the probability that in the sample of students that we took, more than half of them go to college within 50 miles of home. Right, so you might be thinking, but they told us it's 35%. What are we talking about with this half? So keep in mind that what's true for the population is not always going to be true for the sample. What's true for the population is not going to be true for every single sample that we take. So some of the samples might have 35%, but some of them might be less or might be more. And what we're trying to determine is if I take a random sample from that population of 50 students, what are the chances that in that sample, more than half of them live close to home? So that's what we're going to figure out. And the first step that we have to do to figure that out is to make sure that we can accurately describe the sampling distribution for this situation. And that means we have to check those assumptions and conditions. So our first assumption is that we have a random sample. And in this case, we were told, asks a simple random sample. So I can just say we were given the simple random sample of 50 college students. Our second condition is that 10% rule, and that's checking for independence between trials. So I just need to check, does our sample size of 50 seem to be less than 10% of the entire population? You could also do it the other way. Do you think our population is at least 10 times the sample? And that's usually going to be an assumption that we make. In this case, our population would be all the students at the college, all the first-year students at the college. So as long as our population is at least 10 times the sample, so 500 students attending a college first year, that's probably true. Colleges are usually pretty big. So I'm going to say that as an assumption, it's most likely true. So I can say we safely assume that 50 students is less than 10% of all first-year college students. And then our third condition is that large counts condition or success failure. This is what checks to make sure that our sampling distribution is going to look roughly normal. And that's good because it'll allow us to use a normal model to find a probability. So for that one, I check, does n times p, so n is the total number of trials, so 50. P is the probability, which is 0.35 or 35%. So I'm checking, does 50 times 0.35 equal greater than or equal to 10? And it does. And then we check n times q, which is q is just 1 minus p, so 0.65. So 50 times 0.65 is 32.5. Both of those are greater than 10, so that just tells us that our sampling distribution is in fact roughly normal. So here's the thing. On a free response question, we do actually have to write these all out. They don't have to be complete sentences, but they should be complete thoughts. So I don't just want to say like random sample check. I need to actually put some context and some words in there. So given a random sample of college students, assume 50 is less than 10% of all first-year college students. NP, NQ, what they equal, both greater than 10, so roughly normal, something like that. But we do have to actually write out what all of these conditions are telling us, or at least checking them in context. My next step is going to be, now that I know what the shape of the distribution is for the sampling distribution, I also need to know what the mean and standard deviation are. And that's where those formulas from the formula chart come into play. So the first formula tells us the mean, And it basically tells us that the mean of our sampling distribution for p hat is just equal to p. And p, remember, was what was true for the whole population. So 35% was our p, what was true for the whole population. So that should be the mean of our sampling distribution, so 0.35. Standard deviation of that sampling distribution is given by the formula square root of p times 1 minus p over n. So I'm just going to plug in p was 0.35, n is our sample size, which is 50. So I'm going to plug in those values. Then I'm going to do a little math in my calculator to figure out what that equals, which is about 0.067. So that is where my mean and standard deviation come from. I'm just using those formulas. So I have that. So I've got the shape is normal. I know that I can accurately describe my sampling distribution because those other conditions or assumptions pass. And now I know my mean and the standard deviation. The next step is I need to find a probability. And a probability comes from, in this case, the normal model, since I have discovered that this sampling distribution is normal. So I'm going to use that normal model to calculate the probability that I'm looking for. And the probability that I'm looking for is that more than half of the sample goes to college close to home. So what I want is for that p hat, which is the sample proportion, to be greater than half, which is 0.5. So the probability that sample proportion p hat is greater than 0.5 is what I'm looking for. That is my goal for this situation. So I'm going to draw a normal model because I know my sampling distribution is roughly normal. I'm also going to label the two things I know. My mean is 0.35, and then I could, if I wanted to, I didn't on this particular situation, but I could go ahead and draw out 3 standard deviations either way. And using the standard deviation I calculated back here, I could kind of roughly put in some numbers, just add and subtract 3 standard deviations in either direction and label that on the normal model. I didn't do that, but you can. Right, so the next step would be to find a z-score. Right, we draw a normal model, we label it with the mean, and then the next step is to find a z-score. So my z-score formula is we take our observed value, or the value we're trying to find the probability for, minus the mean divided by the standard deviation. So my observed value would be 0.5, right, because that's what I'm trying to find the probability for. The mean of the sampling distribution is 0.35. The standard deviation of the sampling distribution is 0.067. Do that calculation and I get a z-score of 2.24, which means 2.24 standard deviations above the mean is where that 0.5 lands on the sampling distribution. And then I wanted to find out if the probability that more than half of them, so I'm going to shade to the right to represent greater than. At this point, I'm using a normal model and a z-table like I always have. I would go to my z-table and look up 2.24, right? Find that probability, and then remember, our z-table always gives us a less than probability. That's the default of what it gives us. So if I want greater than, I have to do 1 minus the probability that they gave me. So I had to do 1 minus something to get my answer, which is 0.0125, right? And then the last step we're going to do, and this is kind of new to us, usually once you found the answer, you circle it, you move on, but I want you guys to start getting in the habit of interpreting your probabilities. So our last step is to interpret that. And really all I have to do is kind of take the last sentence here and reword it as an answer. So it asks us to find the probability that in a random sample of 50 students, more than half of them go to college within 50 miles of home. So I can kind of take that sentence and reword it as an answer. So there's about a 1.25% chance, or you could just say a 0.0125 probability that more than half of a sample of 50 students lives within 50 miles of home. And that's it. That's my answer for this particular problem. So basic steps for solving this type of problem with sampling distributions. First, we check our necessary assumptions and conditions, and we do have to write them. We don't just like think about them in our head and then write, okay, all the assumptions pass. Like we actually have to write them out. Second is to find the mean and standard deviation of the sampling distribution, and that's just using formulas. Third is to use the normal model to find the probability that you're looking for. And the fourth is to interpret that probability in context, explaining what that probability actually means in the context of the problem. So those are our 4 steps in order to solve a question like this. So there's one last example that I'm not going to talk about right here, but I'm going to leave this screen up. If you want to go ahead and write that problem down and try to work it out yourself based on the steps that we just learned, we will go over this problem in class together next class. All right, see y'all later. Have a good day.